I'm going to talk about the different types of singularities, and I'm going to give you calculus examples because they're easier to draw and easier to draw a graph of and get maybe an intuitive sense of what they're like. So the equivalent of an isolated singularity. So you want to think about singularities as essentially you're dividing by zero, and that causes problems. But in an isolated singularity, you're barely doing it. So again, a calculus example, x squared minus 1 over x squared over x minus 1. Right? So if x is not equal to 1, then f of x is just going to equal x plus 1. If you factor the top, it works out like this. So the graph of this is barely an interesting function. Right? The graph of this looks like, boom, like that. And this is what an isolated singularity is. Yeah, you're dividing by 0 at 1, but just barely. And so what it is it looks like just a regular old function with just a little hole in it where you're dividing by 0. But the rest of it looks completely normal. Let's contrast that with a pole. A pole, an example of which might be f of x equals 1 over x squared, say. The graph of this looks like, boom, boom, like so. So definitely, I mean, something weird is going on here. The function's going off to infinity, which is quality of a pole, and so it's somehow worse than this one. This one you can't plug in 1, but here you can't plug in 0. Oh, the pole's at 0. At x equals 0. At x equals 1. Sure, you can't plug in 0, but you could by just multiplying by a polynomial. So you could, and I'm not sure exactly what this means, but in some sense you could fix this by multiplying by x squared. X squared times f of x equals x squared times 1 over x squared equals 1. And so if that were the case, then everything's pretty much good, and right, you get x squared over x squared, so you still probably shouldn't plug in 0, but then you get kind of a nice function that doesn't blow up at infinity. So this is a pole at x equals 0, and it's of order 2. Because if you multiplied by x squared, you get rid of that pole. Alright, so the last type of essential singularity is, for example, f of x equals e to the 1 over x. So this is going to have some weirdness here. So the graph of this, and maybe I'll actually do this one in color. The graph of this is pretty weird. It's, I want this to be green. Right? So as x goes to negative infinity, you're going to basically e over 1 over negative infinity. Don't tell anyone I said that, but that's basically 1. But then as you get closer, you're going to get smaller, and then you're going to shoot up. Right? As e gets close to, or as x gets close to 0, you're going to get 1 over something really, really small and negative. So, but sorry, I got that wrong. So let's just undo that. So, right, you're going to go towards 1 as you go to negative infinity. But as x goes to 0 from the left, this is going to go to, 1 over x is going to go to negative infinity. But e to the negative infinity is essentially 0, so that's going to go to 0 right there. But as you approach from the right, you're going to get, basically that's going to go to infinity, which is going to be huge, and then get smaller from there. So this is an essential discontinuity, or an essential singularity. And notice x to the n times e to the 1 over x. That's not going to make it any better. That's going to be completely weird. So that's what we have. Isolated means, okay, yeah, there's a 0 there, but it barely affects the function. A pole, you actually do go off to infinity, but if you multiplied by, like, some power of x, you could essentially fix it. Essential is just weird. It's none of the other two. You might go to infinity at one side, and you might go to 0 elsewhere. That's that. Enjoy.